Okay, so the last chapter we're dealing with in this course is chapter 10, and it's all having to do with matrices. We're going to talk about matrices and determinants. Today, we're going to talk about matrices and systems of equations, writing a system of equation as matrices. You might have seen this before. Has anybody done any matrices before? No? Okay. In a sense, you really have. It simplifies things. So in this section, you're going to study a streamlined technique for solving systems of linear equations. Notice we're solving linear, right? So in the last chapter, we talked in section 9.1, we talked about solving systems of equations that involve both linear and nonlinear. And then we moved into elimination. We just only looked at linear. When you're dealing with matrices, we're only going to look at linear equations. We're going to use a rectangular array of real numbers, and that's called a matrix. The plural of matrix is matrices. There is what a matrix looks like. If M and N are positive integers, then an M by N matrix is a rectangular array. Each entry, A sub ij of the matrix is a number. An M by N matrix has M rows and columns. It's always rows first, rows, then columns. M by N. Matrices are usually denoted by capital letters. So in row 1, this very first element, that would be A sub 1, 1. I'm in row 1, column 1. So row 3, column 2, that would be A sub 3, 2. Row 3, column 2. And a matrix can be anything from a 1 by 1 to a n by n, or m by n, because they don't have to be, it doesn't have to be a square matrix. The entry in the ith row and the jth column is denoted by a double subscript denoted as A sub ij. For instance, A sub 2, 3, that means second row, third column. A matrix that only has one row is called a row matrix, and if it only has one column, it's called a column matrix. Mathematicians are really, really creative in naming things. A matrix having m rows and n columns is said to be of order mn. So when I ask about the order of a matrix, I'm talking about the dimensions, okay? Those words can be interchanged. Usually I say dimensions, but I know on the homework it actually says order. I think I just skipped a slide. I did not. Okay. If m equals n, then it's a square matrix. Makes sense, right? If m and n are the same, it's a 6 by 6 matrix. It's a 3 by 3 matrix or whatever. For a square matrix, the entries 1, 1, 2, 2, and 3, 3 are the main diagonals. And let me go back a couple slides. Here. So if I just looked at this part right here, that would be a 3 by 3 matrix, right? 1, 1, 2, 2, 3, 3. That's your main diagonal. That's important. Understand where that main diagonal is. Okay. So letter A, what is the order of that matrix? 1 by 1. One row, one column, right? So letter A, that is a 1 by 1 matrix. Letter B, 1 by 4. Letter C, 2 by 2. Letter D, rows first would be a 3 by 2. Okay, so make sure you get them the order right. Always rows first. Again, order means dimensions. Moving along. A matrix derived from a system of linear equations, each written in standard form with the constant term on the right, is an augmented matrix of the system. This is a system of three equations. We have three equations. How many unknowns do we have? Three unknowns. Can we solve a system of three equations and three unknowns? Yes, we can. Okay. This is augmented when it includes the answers. Notice that the x's are all lined up, the y's are all lined up, the z's are all lined up, and the constants are on the right side. If I wrote a matrix with just the coefficients, it would be called a coefficient matrix. So let's go ahead and write the augmented matrix here. Augmented. Someone look up the definition of augmented. Just an English definition, see what it says. Okay. So put together? Put together? Okay. So then augmented matrix is actually two matrices that are put together. Okay. I'll turn. Ow. Very funny. Yeah, it is. Okay. So the augmented matrix, I'm going to totally ignore all of the variables. Okay. So my first row is going to be 1, -4, 3, and 5. My second row would be, you tell me, -1, 3, -1, -3, and the third row, 2, 0, -4, and 6. Now, many times when you have an augmented matrix, you'll see like this dotted line that separates them. Okay. But as you're doing the work, you probably won't write that dotted line. You'll just know that that last column is going to represent the constants. So a matrix derived from the system of linear equations is the augmented matrix. So this is the augmented matrix of this system. The matrix derived from the coefficients of the system, but not the constant terms, is the coefficient matrix. So that means that this part right here is the coefficient matrix. Okay. What is the order of my augmented matrix? Three by 4. The order of the augmented matrix is 3 by 4. 3 rows, 4 columns. What is the order of the coefficient matrix? 3 by 3. 3 rows, 3 columns. What's this last thing? Okay. I don't remember what this text calls it for sure, but I know in the past I've called it the solution matrix. Which happens to be a column matrix because it only has one column, right? What's your question, bud? Because it's a combination of the coefficient and the solution matrix. Yes, the augmented is put together. Any other questions on what we've talked about on this slide? Okay. There's the augmented matrix. There's the coefficient matrix. And I'm moving on. Notice that where that last row, we did not have a y term. So because there was not a y term, we had to put a 0 there. Okay, anytime there's something missing, you must put a 0 in that place. Something's got to hold that position. When forming either the coefficient matrix or the augmented matrix of a system, You should begin by vertically aligning the variables in the equations and using zeros for the coefficients of the missing variables. Any questions so far? Y'all feel comfortable that you can make a matrix out of a system? Okay. Okay. We're going to talk about some elementary row operations, and we've already done this. Even though we didn't use matrices, we've done all of this. The first one, not so much. So the three operations that we can do. If I had a system, does it matter which order I write the equations in? There are three equations, right? So that's what number one is. Number one says I can exchange the equations, and it still means the same thing. Number two, you can multiply an equation by a non-zero constant. Did we do that in elimination? Right? We would multiply it because we wanted to eliminate a variable. We would multiply one of the equations by something, or sometimes both equations by something. Number three, we can add a multiple of an equation to another. Did we do that? We would take an equation, multiply it by something, add the two equations together, bang, something gets eliminated. Guys, we're doing the exact same thing with matrices. In matrix terminology, these three row operations correspond to elementary row operations. These are the basic things we'll be doing. All right. An elementary row operation on an augmented matrix of a given system of linear equations produces a new augmented matrix corresponding to a new but equivalent system. Two matrices are row equivalent when one can be obtained from the other by a sequence of elementary row operations. Okay, look at this notation. If I want to swap two rows, I would say R sub 1 with an arrow pointing both directions, R sub 2. That just means I'm going to take row 1 and row 2 and swap them. If I want to multiply a row by a non-zero constant, I would put that constant in front of the number, in front of the row. For instance, 4 R sub 4 would mean take row 4 and multiply it by 4. Okay? If I wanted to add a multiple of one row to another, I would say 3 R sub 2 plus R sub 1 means take 3 times row 2 and add it to row 1. Okay, pretty obvious. Okay. So this could be like a homework assignment that has 9 answers on it. That's why this homework assignment has like 153. A bunch. Okay. This would be 12. This problem says to interchange the first and second rows. So what are you going to do? Okay. Okay, we're going to do R sub 1 swapped with R sub 2. And what's that going to look like? That'll be the top row, and then that row, and that, does that one change? No, we did not mess with this row. Leave it alone. Okay, so that's what that looks like. This is hard stuff. Now we'll talk about it again, but when we're doing this, our goal is to get this main diagonal to be 1s. Everything below it needs to be 0s. Okay, so that's where we're headed. Previous slide real quick. That wasn't the steps. You want the notations? All right. Here's another problem with 12 answers. Multiply the first row of the original matrix by 1/2. What's that notation going to be? What's the notation of what we're going to do? 1/2 R sub 1. So is R2 changing? Is R3 changing? Okay, that's 8 answers you got right just by copying them. So when you're doing the homework, understand that the 114 is not a big deal. Okay. Okay. So what is row 1 going to be? Okay, this is hard stuff. Okay. Again, our goal is we want 1s in this main column and we want 0s everywhere else below it. We'll talk about what that means in a minute. Moving on. C says add -2 times the first row of the original matrix to the third row. -2 R sub 1 okay. Which row is changing? There's only one row changing. Just the third row is changing. Just the third row. Now, when I'm doing this, and like I said, I sat down and I did the assignment, that long problem that has all the problems in it, and I made a careless error in like the first step. And because I did that, there were a bunch of errors that followed there. But I did not write anything down as I was doing it. So I'm going to tell you, when you're doing it, write it down and you won't make the stupid mistakes. So the first thing that I would do is I would say, well, I want to take -2 times R sub 1. So let's do that real quick. What would row 1 be if I took -2 of it? Okay, now, am I changing row 1 for my answer? No. But I'm going to use those numbers to combine with row 3, right? So what's row 3 going to end up being? Does that make sense? Do what? -6 and -2 is -8. Okay. Row 1 stayed the same. Row 2 stayed the same. Row 3 changed the numbers that we had. Off to the left side, what we did. This right here, nice. Okay, this is what we did to the third row. This is just so that you can pay attention to what you're doing. We can work on 2 rows at the same time, and that's okay. But put off a little note to the side on what you did to make that change happen. Any questions so far? The term echelon refers to the stair-step pattern formed by the non-zero entries of the matrix. To be in this form, a matrix must have the following properties. We're working on putting a matrix in what's called echelon form. To be in echelon form, the main diagonal has to be 1s. The numbers below those 1s are going to be 0s. Okay, so here we go. Row echelon form, and then we'll talk later about reduced row echelon form. A matrix in row echelon form has the following properties. Any rows consisting entirely of 0s occur at the bottom of the matrix. So if at any point you have all 0s, move it to the bottom. Step number 2, For each row that does not contain entries of zeros, the first non-zero entry is a 1. For two successive non-zero rows, the leading one in the higher row is further to the left of the leading row in the lower row. Does that make sense? So if row 1 was 1, 6, 2, 3, to be in row echelon form, what does this number right here have to be? A 0. What does this number have to be? What about these numbers? Doesn't matter. Let's do another row. 0, 0, 1, doesn't matter. Okay. The thing about this is if we can get a matrix into row echelon form, we can use back substitution and solve it. Okay. A matrix in row echelon form is the reduced, a matrix in row echelon form is in reduced row echelon form when every column that has a leading one has zeros in every position above and below its leading one, which means, so this would be row echelon form. Reduced row would look like this: 1, 0, 0, some number. 0, 1, 0, some number. 0, 0, 1. I'm going to go ahead and put an 8. And I wrote it this way to show you these are the same. I just don't know what number goes in those, but I know that one's an 8. And we'll talk about what all this means later. So this is row echelon. This is reduced row echelon. If a matrix is in reduced row echelon form, just by looking at it, you know what X, Y, and Z are. If it's in row echelon form, all I know is I know Z is 8. Okay. It's okay if it doesn't fully make sense yet. What does number 2 mean? For each row, so we're talking about row echelon form, for each row that does not consist entirely of zeros, the first non-zero entry is a 1. The first entry is a 1. The first non-zero is a 1. The first non-zero is a 1.
So, like it's saying if there is a 0, the first real number has to be a 1.
Yes. It is possible that you have a row of all zeros. Obviously, in that case, you don't have a 1. That's what it's saying. Other questions? Okay. It is worth noting that the row echelon form of a matrix is not unique. All of us could be doing the same system of equations. And if we write our equations in a different order, maybe one of us decides to swap because we like it that way better. Row echelon form and your row echelon form might not be exactly the same. But if we did reduced row echelon form, we would all be exactly the same. Row echelon form will get us all to the exact same answer, but row echelon form will not be the same for everybody. Two different sequences of elementary row operations may yield different row echelon forms. However, the reduced row echelon form is unique. Unique means there's only one, right? You are unique, just like everybody else. Huh? Okay. Gaussian elimination with back substitution works well for solving systems of linear equations by hand or with a computer. For this algorithm, the order in which the elementary row operation is performed is important. You should operate from left to right by columns using elementary row operations to obtain zeros in all entries directly below the leading ones.
I don't like that it's called elementary row operations. Now I feel stupid.
Okay, so here's a problem. We're going to solve it. So to solve this problem, we are going to start by writing the augmented matrix. Okay. How many rows? 4. How many columns? 5. Okay. I don't think we're going to solve this one all the way. What's the first row look like as a matrix? Can you reorder it? You could.
Why? Well, and W comes before Y and Z.
Oh.
We're changing it to number.
0, 1, 1, -2, -3. 0, 1, 1, -2, -3. Next row.
1, 2, -1.
Perfect. Next row.
2, 4, 1, -3, -2.
Okay. And finally.
1, -4, -7.
Okay. Now, you're not going to be responsible to solve a system like this. Okay. That would be cruel and unusual punishment. Okay. Yeah, maybe we're going to go a little further. So here's the matrix we came up with. So a good step to do this is, remember, we want the main column to be ones, correct? Or the main diagonal. Well, that can't be a 0. That needs to be a 1. So what's the easiest way to make that a 1?
You flip them with the second row.
Okay. What if someone wanted to put the fourth one up there? Can we do that?
That's why you can get different words.
That's why we get different answers. That's why we could have different answers. Okay. So, and I left what they did here to make sure that we do what they did. So when we swap row 1 and row 2, is that a big change for us? We just write down this row, then this row. What about 3 and 4? Leave them alone. Okay. All right. Look what that did for us. A 1 and a 1. Oh, that's already a 1, so we're good to go, right?
But the last one's a negative.
But these have to be zeros.
Oh, that's
Yeah, second row is good to go, but I was saying there's a 1 already here. Does that mean this third row is good to go? And the answer is no, because the first non-zero has to be a 1.
matters on the bottom row that the like the -1 is negative, or does it have
That one?
Does it have to be positive?
Well, these have to be zeros anyway when we get done. Okay. So my question for you now is, that needs to be a 0. How can I turn that 2 into a 0? Then everything's 0.
You add -2 R4.
That would work. Okay. The best way to do this is, once you have the first row like you want it, use that equation to change the numbers in that first column to zeros. I want to keep that 1. That's already a 0, so I'm happy. I want that to change into a 0, and I want that to change. So if I take -2 times row 1, that would give me a -2 right here. It's now row 1 because we swapped them. Whenever you give it a name, you're talking about the previous one.
Is it always going to be that?
Do I? 1 second.
Are you always going to do that? Like, go for, like, flip up and then use that equation?
You're going to use whatever the first equation is. Once you get that a 1, you're going to use that equation to make the ones below it zeros. And then we're going to use this equation to make those zeros. Because once these are zeros, adding nothing to it is going to leave them with zeros. Okay, so notice we're going to do 2 steps in 1 here. I'm going to take the first equation, which is my new row 1. I'm going to multiply that row 1 by -2. And again, I say write it down. So I want -2 times row 1, which gives me -2, -4, 2, 0, -4. This is -2 row 1. This is row 3. Okay? So if I combine, let me just go ahead and move this down a little bit, because we're not doing anything to row 1 and row 2. We're leaving them alone. Okay. So if I combine these, I get 0, 0, 3, -3, -6. 0, 0, 3, -3, 6. Now I'm going to use row 1 to get rid of that 1. So I'm going to take row 1 and multiply it by -1. So negative, nice. I know. So -1 gives me -1, -2, 1, 0, -2. I'm going to combine this purple row with row 4. -1 and 1, 0. -2 and -4, -6. 1 and -7, -6, 0, -1, -2 and -19. How are we doing? Y'all following this? My first non-zero is a 1. My first non-zero is a 1. My first non-zero, not a 1. How can I turn that into a 1? Multiply it by 1/3. So I'm going to multiply this whole row by 1/3. Okay. What do I need to do to this -6? It needs to be what? It needs to be a 0. How can I make this a 0? Just randomly, just add 6 to it, make it go away. I want that to be a 0. If you multiply by 0, the whole row's gone. That's not good. Okay. Look up here. How can you use row 2 to get rid of this? Multiply by. That'd be a 0. That's where we're headed. Let me go to the next slide. This is still easy. Okay, so here's the matrix that we're left off with on the previous slide. First thing I want to do is they want to get rid of this. So I don't want to add row 1 to this because that would reintroduce 1s in column 1. But I do want to get rid of that -6. So if I multiply row 2 by 6 and add that to row 4, that'll turn this into a 0, right? Yeah, it's a nice thing here. So I'm going to take row 2 and multiply it by 6, which gives me 0, 6, 6, -12, -18. 0 combined with 0, 6 combined with -6, 6 combined with -6, -12 and -1, -18 and -21. Okay, there you go. Notice my main diagonal has numbers in it. and everything below the main diagonal is zeros. So we're almost where we want to be. But the main diagonal has to only have ones in it. So I need to turn that 3 into a 1, and I do that by 1/3. I need to turn this negative 13 into a 1. Multiply it by negative 1/13.
Why didn't we start to solve before we fully solved the 30? Like, couldn't we have just?
I mean, we could have done the 1/3 part first. Okay. When you multiply row 3 by 1/3, I did it again. If I multiply row 3 by 1/3, I get, okay. And if I multiply, so we got 0, 0, 1, -1, -2. If I multiply the last row by negative 1/13, I get, okay. Can you tell me the value of W? W is 3. W is 3. Think about what the matrix started with. These were my X coefficients, my Y coefficients, my Z coefficients, and for whatever reason, my W was last. These are my constants, which means 0 X's plus 0 Y's plus 0 Z's plus a W is 3. Therefore, W is 3. So now that we know that W is 3, I can take that value of 3 and plug it into this equation and have Z minus 3 equals -2. And that would give me Z. And then I could take those values and plug it in here and just keep plugging them in going backwards, and I'd have the whole system solved. Okay. So here is the matrix in row echelon form. Using back substitution, we find that X is -1, Y is 2, Z is 1, and W is 3.
Yeah, I definitely out of all lessons. You're saying you understood the logarithm.
Yeah, not, I didn't say the last one. I said
Okay. The procedure for using Gaussian elimination with back substitution is summarized below. Gaussian elimination with back substitution. Number 1, write the augmented matrix. Step number 2, use very simple or elementary row operations to rewrite the augmented matrix in row echelon form. Step number 3, write the system of linear equations corresponding to the matrix in row echelon form and back substitution. That's it. When solving a system of linear equations, remember that it is possible for the system to have no solution. If in the elimination process you obtain a row of all zeros except for the last entry, then there's no solution or it's inconsistent. So if we had a row that looked like this, so we got a bunch of stuff going on, and then we got this 0, 0, 0, 4. Okay. What you just told me is 0x plus 0y plus 0z is equal to 4. Really? Does nothing equal 4?
No.
Okay. With Gaussian elimination, elementary row operations are applied to a matrix to obtain a row echelon form of a matrix. A second method called Gauss-Jordan elimination continues the reduction process to reduce row echelon form. So we could keep doing this process to get reduced row echelon form. Okay, so here's an equation. Here's a system. And, I know. And you just have to trust me on this, that this system was worked using elementary row operations to obtain this matrix.
I'll take your risk.
Can you see If we took equation number 2 and multiplied it by 2 and added it to equation number 1, that would be a 0. Okay. Could you see that we could take row number 3, multiply it by -3, add it to row number 1, and this would also be a 0. In doing so, we would have 1, 0, 0, and then whatever we ended up with over here. Okay. So we'll continue from here tomorrow.